Our task here is to create a function that models this situation. We have a roller coaster, and we have to make a function that shows the motion or the movement of the roller coaster. And when you read the opening paragraph, it tells you what to do. The first thing you want to do with every modeling problem is to make a sketch of what your function should look like. So if this is the ground, and this is the height, then we have a height axis, and we have a distance along the ground. I'll just call it x. And it says that the roller coaster will run for 200 meters. So if this is our 200 meter mark, and 100 would be around about here, and we want to have a maximum height of about 70 meters. So let's say this is 70. And let's just see what we have to do. So at about the 60 meter mark, we have to get to the height of about 70. So approximately 60, we need to be up at a maximum height somewhere up here. And then it says drop to a height of about 10 meters off the ground, but it doesn't say where. So somewhere in here we have to come down to about 10 meters. And then it says rises one more time and comes back to the ground. So let's assume that we start on the ground, gentle, and then roller coasters go up, and then it must sort of max out somewhere here. That's probably not going to work. It's probably more like this. And then it's going to come down to around about 10, and it's going to go back up again, and then it's going to come back down to the ground. But we want it to be a gentle landing. You don't want to smash into the ground, so it should be like this. So that, when you look at that picture, that looks like a polynomial function. We've graphed lots of polynomials, so we're pretty good at graphing them and figure out their equations. So just to look at a couple of key features here. In this area here, let's use green, we are going to want to have one of those multiple zeros because we want to flatten out at the ground. If you don't do a multiple zero, then you're going to go straight through, and it's going to come down at a sharp angle. We don't want that. So we want to have a smooth curve there. Same thing at the end. We want to make sure we have a gentle landing on the ground, so we'll even it out. It'll have to be a multiple zero, so probably a squared of the factor. One interesting challenge is this part here. I want it to be a zero, but it's not to be a zero. It has to be a value of 10. So how do I do that? It looks like we're at about 120 on the x-axis here. This is just ballpark. It doesn't say you have to be exact in this problem. You can do whatever you want. So I'm going to say it's 120. And so if we look at what we've got, from this part here of the graph, we need to have an x squared term. And from this part here, we need to have an x minus 200 squared term. And then here, what are we going to do? Well, if we were touching the ground, we would have this. But we're not touching the ground. So an idea is, what if you raise it up by a certain amount, maybe 10? I have no idea if 10 is going to work. And I don't even know if the whole idea is going to work. But I'm going to give it a try in Desmos. So I want to type that all in, multiplied together. So here's Desmos. If I say that my function is equal to x squared times, let's just see what we had. So, okay, x minus 120 squared, and that doesn't look right. Hang on. And then that's going to be on the outside of the bracket. So like this. And then we want to put plus a number, and then we're going to go x minus 200 squared. Okay, so Desmos isn't showing us very much here, but that's because our scale is terrible. So we need to adjust the scale. First of all, I want this x scale to go up to 200. So there's 200. And then I want the y scale to scrunch down so that I go to my height of about 70. So the graph, you can't even see what's going on here, but I think that's because it's so awfully high-reaching. So what we need to do is vertically compress the graph, or use a very extreme extremely small stretch factor, so like 1 over 100. Okay, well, the graph still isn't in view, so I'll make it 1,000. I'll make it 10,000. I'll make it 100,000. I'll make it 1,000,000. I'll make it 10 million. I'll just keep putting zeros until the graph comes into view. Okay, here's our graph, and it's now in view. And it is doing what we want. That's pretty much what we want, except the maximum height is not 70, and it's not high enough at the 120 mark. So if we go in here and just play with the numbers until it looks good, maybe 30, maybe that's just not enough. Maybe it needs to be more like 100. Okay, we're getting it off the ground anyway. I'm going to have to play with that number a bit. The other number I have to play with is the vertical stretch factor. So right now, where our maximum height is around, it's just under 30, and we need it to go to 70. So if I just multiply that top number by 2, and a bit more than 2 actually, so maybe make it 3. That's too much, so maybe 2.5. That's pretty good, that's about 70. And if we look at this 120 value right around here, that's at 2.3, but I want it to go higher, so I think I have to adjust this add-on number. Maybe 200, no, maybe 300, maybe 400, maybe 450. That's pretty good. We're at 10.28. The maximum height of the function is now too high, so I'm going to scale that 2.5, factor it down a bit, maybe make it 2.4, maybe make it 2.3. And if you look at the curve, I think that really satisfies the conditions that we're supposed to get. We're supposed to start at 0. We're supposed to go up to a highest point of about 70, drop down to about 10 meters off the ground, and then have another bump, and then have a soft landing. So we've just got our function here. It seems to work. The next thing you have to do in the problem is calculate some y values, and since I typed in f of x here, I can now just do f of a number. So if we want to do f of 60, then we can get our value there. If we want to do f of 70, we can get a value there. And if I want the slope between those 2 points, first of all, let's get the points to show up on the screen just so you can see what I'm talking about. So there's our point 60, f of 60, and we want the point 70, comma, f of 70. And then if we want to calculate the slope, we could just do the slope between those 2 points. We could do f of 70 minus f of 60, and we divide that by 10, and that would give us the slope. Now it's up to you to interpret these values. That slope of negative 0.954 would be the rate of change of height with respect to horizontal distance. So the negative sign means that the roller coaster is descending at that point, and it's dropping at a rate of just under 1 meter of elevation for every 1 meter of horizontal distance. So about a 45-degree angle, really. It doesn't look like a 45-degree angle here on my diagram because I don't have the same scale on x and y. So I hope that helps you to figure out how to model this function.